The space is not a program.
Mm-hmm.
Space is a place.
Uh-huh.
Most people see space as a program. We printed until the last possible moment, and then we let go of the Skylight, and the Skylight kind of landed, and then it did a. Now that space stations have been technically solved, they can still be improved, just like rockets were solved 50 years ago. The hardest thing now to solve for is the business of commercial space, especially human spaceflight.
Welcome to the OAP028 podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, OAP028, and today I'm thrilled to be joined by Jeffrey Montes. Jeffrey is a senior space architect who has been at the forefront of designing our future in space, from award-winning Martian habitats like the Mars Ice House and Marsha to architecting the Orbital Reef space station at Blue Origin. Jeffrey, it's great to have you on the podcast.
Pleasure's mine.
There's a perception among some in the industry that despite all the stunning concepts produced over the decades, space architecture could be in a state of failure to launch. From your position, how much truth is there to that statement? Is the field stalled or maturing, and why?
It's early. I mean, just to give you a sense, I personally know and count as a mentor someone who remembers Sputnik launching.
Okay.
So that tells you that there are still people who are alive, not only alive, but lucid, who remember, who have in their memory the entire space age. It's very early. If I think back, and unlike other nascent industries, this one moves slowly because of it's not like, oh, space is hard. Yes, it's hard, but it's just like on a pure physics level, the energy intensity required to successfully get something into space, to get it to get data down to you, to be able to learn. The learning cycle is slow compared to other industries. And there's many reasons for that. So in a way, it's like, yeah, we failed to launch. We're all there's a sort of disappointment meme in space flight
Feels like
is
a bell curve.
yeah. I mean, look, there are waves, and the waves are highly contingent on things that are much larger and outside of the control of the people and the who have hopes and dreams inside of the field.
So
I don't know if people know, but the space station passed Congress by one vote. Imagine if one person had voted differently. It's not only would the history of spaceflight, things that have flown in space be very different, but the industry as if you think of the industry as a set of people and as a workforce would be far less developed. So all the things I learned at Blue Origin, for example, that trickled down from the knowledge of people who had figured this out in the 80s and tried very hard to make it a reality. Some of them succeeded, most of them did not, or many of them succeeded partially. Probably everyone failed in some way to actually see the things they wanted to fly. And
yeah, exactly. And we're also seeing the aftermath we're still experiencing the aftermath of the corona. Yeah.
In many ways.
So before we dig deeper, how do you define the discipline of space architecture?
Well, I won't give you the official definition because it's not that interesting. It's just, architecture in space.
Yeah.
But maybe I think the best way I could put it, which I actually have to credit to someone else who I spoke with recently, just as a succinct phrase, is that space is not a program. Space is a place. Most people see space as a program. They see it as a set of things that occur. And most of those things are scientific. The program is you have a certain kind of person doing a certain kind of thing in a certain kind of environment, and that's what space architecture is. But it's not really what space architecture posits, and I guess has always believed, is that space is a place just like any other. It's accessible. We can get there. We can live there. It has environmental conditions, and those, a lot of a lot is made of those environmental conditions because they are so different, and they're dialed up to 11 or dialed down to -1 or whatever it is compared to Earth. But it is just a place, and the more that you, I guess, work in that field and just like work as an architect or as a designer in that field, you you start to just, it becomes normal to you. It becomes just like, yeah, I'm yeah. I guess when people, there was a point in my career, maybe earlier in my career, when people would ask me what I did, and I would say I'm a space architect because, how cool is that, right? And I'm special, and I do something that's different. But as time went on, I just realized, no, I'm an architect. Like, I'm an architect. And then when they ask me, well, what kind of architecture do you practice? Then that's when I tell them, and they're like, whoa, I didn't know that was, and then the conversation begins. But it's almost like I'm first and foremost operating as an architect, and it's obviously, as there's two parts to that. There's the places, you know, that's the part that's in space, but then there's the architecture part, which occurs in a context on Earth, like a social, cultural context, technological context. And that's where, maybe half of your time is spent on the, how do you even practice in this environment. I don't mean in space, I mean like in an office building on Earth, but surrounded by the certain type of person. And then the other half of it is like, well, okay, let's think about the space part now, because that's like outwardly inspiring part of it.
Okay. So if we look at the job titles across the aerospace industry, including at NASA, the specific title of space architect is rare or even doesn't exist. Is there a fundamental gap between your definition of the role and how the aerospace industry currently perceives and utilizes it?
Yeah, I mean, I think before the term space architect was, I guess, formally defined at the AIAA, it was often used. It was used as a phrase, but it meant something different. It didn't mean architecture in the classical sense of buildings for humans, structures for inhabitation, but it really just meant more like, what is the architecture of our mission in space.
Okay.
So a space architect at one point would have been considered to be a mission architect, essentially. And a mission architect has a sort of temporal and spatial and engineering view of an objective, and they understand that in order to achieve something in space, pick a destination, you need a certain kind of high level performance. Then you can break that down into different vehicles that perform different functions at different times. And then you have to basically almost work backwards and orchestrate this whole thing, which, involves launch. It involves specific orbits. It involves burns, propellant burns, maneuvers. It involves spacecraft getting, mating and hard capture, soft capture, like refueling, comms links, all the way to, the fulfillment of primary objectives and secondary objectives. And I still encounter people who put space architecture in quotations because they have realized that what I mean is different from what they used to mean. And so it's kind of their way of acknowledging that.
Okay. So there's a persistent stereotype that architects in aerospace are focused on aesthetics after the real engineering is done. How often do you encounter that perception? How often did you encounter that perception? How do you counter it in a room full of systems engineers?
It's prevalent. Yeah, it is. It is prevalent. It's basically like it's a product of innocent ignorance. It's a product of also tactical convenience. And what I mean by that is, okay, people don't really know that. Some people don't even know what architects do on Earth. They think of them as something that you're forced to hire because you need a permit. You need drawings to get a permit to, renovate your house. And if you trigger certain requirements in your construction, then you have to hire an architect because, okay. A lot of people will go straight to a contractor, and because they think that they know they think that their high level requirements are enough to have a successful project and actually even satisfy their own, I guess, implicit desires. So you, let's say you move into a house and it's too small, and you think, well, we're a family of 4. We need a second bathroom. Like, this is really annoying, and I've always wanted to have a sauna, and I've always wanted. And then you basically have a list. It's a list.
Mhm.
It's a checklist of things that you would like to have, and you want to go get them. So you ask first the person who's going to be the bulk of the cost of the project is the person who's going to build it, because materials and labor of construction dominate. So you go to them, and if they're a good contractor, they're going to say time out. You don't have an architect, because you don't know how all this comes together. You don't know, if you haven't figured out all the details. You haven't figured out what kind of space you want. You haven't figured out like how you want the space to like actually work in your daily life. It's not put the bathroom anywhere. It's put the bathroom here. And in order to do that, you got to affect everything around it. You have to understand how the building systems are living inside the walls and the force flow of structure. So like think about how like even in a typical setting, people will kind of forget the role of an architect. So that's kind of the innocent ignorance part of it. The tactical convenience is really about, well, if you don't have another cook in the kitchen, you can kind of just make decisions quickly. And so I think that unfortunately a lot of it comes down to that. It comes down to, well, is that another person we have to add to our meeting? And there is a sense of otherness about someone who is not a systems engineer, which is kind of the sort of the, I guess, like the standard token of aerospace workforce is like the systems engineer.
Okay.
If you don't know what someone does, you can call them a systems engineer. Some people are actually systems engineers. Other people's are kind of, I don't know, disguised as systems engineers. But it's a broad enough term that it creates a bit of a fraternity of systems engineers. And if you're an architect, there's this sense of like, oh, a connotation of perhaps authorship, a connotation of sort of overseeing, a connotation of maybe even ownership, not authority, because I never really had much authority, but that's a different question. But I think that's kind of, when you talk about aesthetics, yes, aesthetics is a term that is thrown around, but I have a bit of an unorthodox view on aesthetics. Maybe not unorthodox in the art world or the architecture world, but certainly in the space architecture world, I think people have kind of rushed to denounce what they do as aesthetics, because it does have this connotation of a veneer. It has a connotation of it's just how it looks. But I'm gonna stand up for aesthetics here. Aesthetics is not about looks, it's about experience.
Okay.
And experience is inseparable from performance, functionality.
Yeah. And
For
experience
so
is
many
human-centric, right?
Yeah, like even if you pretend that even if you pretend that aesthetics is 100% optional for a second, and you just say, well, aesthetics is secondary. First, we have to get functionality down. Well, the process and like the approach to making functional systems is tied to how people operate, how people feel about things, how they respond to things. And you can force people to act certain ways through training. You can train them to operate a poorly designed system very well if you just throw time and money at it, and you build simulators and mockups and other training things. So I think aesthetics in a way is something we should own. We should not be like, oh, I'm not just aesthetics. But it's like, well, what if I was just aesthetics? What would that include? And then you realize, you decompose aesthetics, you realize that it includes appearance, it includes feeling, it includes the And what does a experience include? It includes everything. So so I love aesthetics. I think it's obviously there are there are I think what is meant by the derision of aesthetics, or you just do aesthetics, is that we're doing what you like. We're doing what you feel like doing. But if a designer and if a designer cannot remove their own aesthetic sense from I guess the functional consequences of what they're doing and the practical operational, and even I guess risk related, safety related, welfare related, all these things from their own sense of I guess visual pleasure, for example, because most of design is visual. I'm not saying that as a I'm not saying that as in a normative way. I'm saying it in a descriptive way. It's we're a visually oriented species. That is our most powerful sense. I think that that's kind of what happens with aesthetics, is that people tend to flatten it to the way things look in a picture, and that's maybe like a bad route to take as a designer, is to be overly indexed on what you personally resonate with, because those are very subjective. But at the same time, it's so important to have a, let's say, a theme in your work, I think. And that's something that an architect does bring, a sort of spatial theme, an experiential theme, a visual theme. These things are powerful, when you get them right, when they mesh with function and system performance.
So what theme do you think best describes your approach to architecture for space stations, let's say?
I'm a fan of spatial gestures, if that makes sense. I'm a fan of unifying forms. And when I say gesture, I think that that's one of those things that is certainly not aerospace speak, But in the design world, the gesture is almost think of it as a hand gesture, but the hand has a pen, or a pencil on a paper. So personally, I'm always looking for strong, simple gestures that organize space. And if what is the most economical single gesture that could give you the most, I guess, spatial intelligence, if that makes sense.
Yeah, it makes sense. And I think your early project's called Charrette. Yeah, that speaks about the gesture, right?
Yeah, I mean, Charrette was a really interesting student project. It was taught by Chuck Hoberman, who designed the Hoberman sphere.
Yeah.
And that was very cool to have a class with him. So he basically gave us these sort of scissor mechanism, and he asked, and the project was a group project with Chen Yu Pu and my wife, actually my now wife Denai Vokalos. So that was we decided to make a sort of architectural scale iris, or aperture, and apply cladding to it. So yeah, I mean, I never thought of it as I never connected it to the gesture idea, but it's true that there's a single operation that triggers this sort of blooming geometry.
Yeah.
These days, I don't think too much about kinetics, or at least kinetic novelty in that way. And I think maybe it's the same reason architects famously dress in like black and don't use color. Yeah, it's pragmatism, and it's also just like, let's get the basics really right,
So you've spoken about being driven by the concept of technological sublime, which is a sense of awe in the face of immense technological and natural power. What does the technological sublime mean to you? And can you share a moment in your career where you felt you successfully captured that sublime quality, translating it from like a philosophical idea into a tangible design choice?
It was actually, yeah, my very first space project was as a graduate student, and it was my second year of grad school, and it was in my first year of grad school that I even learned about this studio being offered. And that was the moment that I I was like, of course space is a place.
Mm-hmm.
Why didn't I put those things together? It seems so silly in retrospect that I had only thought about space as a kind of a program. I knew there was space flight. I knew there were astronauts, and of course, who doesn't? Who knows?
Mm-hmm.
Who doesn't know that there's a space program? And then I knew there was a space station. But it really kind of is a parallel world. Like if you're not maybe paying attention to it, it could be it kind of is irrelevant. It could be irrelevant to you. So it was at that moment that I put that together,
Mm-hmm.
and I was fortunate enough to have that opportunity in school, because school is the place you're in to be outside of society
Mm-hmm.
and to have total intellectual mobility and not be asked to be practical, not be asked to just constrict your thought process. It's this is what I think school ought to be
Mm-hmm.
is, and I didn't really appreciate that in undergrad. I didn't appreciate that the privilege of being in school was that you're actually outside of society.
Mm-hmm.
You're paying a lot of money to be outside of society, but you're nonetheless there. And like, what are you going to do with that privilege? Are you going to be like patting your resume all the time, or are you going to be thinking and reading?
Mm-hmm.
When I got the opportunity to do the space studio, this was at Columbia.
Mm-hmm.
I had basically total freedom to like make a space project, and the thing that really did kind of hook me was the technological sublime, the philosophy of just what it like the the seeming importance of a human being leaving the planet that it had been basically confined to
Mm-hmm.
for all of history and before. That just struck me really hard, and it felt like it brought out some really great reflections.
Mm-hmm.
I think maybe one of the catalysts in that studio for me was discovering this work of art, this art project by Trevor Paglen
Mm-hmm.
called The Last Pictures. The
Okay.
Last Pictures was basically a curated set of photographs that were etched onto silicone and placed on a geostationary satellite. You're familiar with the golden record.
Yes, of
Everyone's
course. Yeah.
probably familiar with this
Carl
actual
Sagan's
vinyl
design. Yeah.
golden record that was
Mm-hmm.
placed on the side of Voyager as it went off on its tour of the solar system. Trevor Paglen kind of produced a bit of a reaction to that. It was a bit of a response to the golden record, which had a lot of like sort of optimistic tones to it. A lot of, I mean, his assertion was that the golden record was a little bit rosy, a little bit like not. It wasn't really showing us showing who we really were. It was kind of like, here's a picture of us drinking water, and here's the songs of the world, and here's the anatomy, and here's their DNA. Like here's our location. Should you want to visit? It was kind of like a very certain kind of hello,
Mm-hmm.
and his hello was far darker. It was like, and I was inspired by his book. I was inspired by his talks
Mm-hmm.
that I found online. And I guess what struck me at that moment was how things in space persist. That we think of things in space as being so harsh and so, hostile. But when you put a spacecraft up there, it basically just doesn't go anywhere. It lasts forever,
Yeah.
essentially. Like,
Yeah.
and he had this line where, if you a geostationary satellite it was in the early days of spaceflight, when there was lots of satellites going up, there were estimations that satellites in geo would last like a million years or more. And I don't think that's exactly correct today. I think it's more like 10,000 years. Essentially, there's no drag up there. They'll stay up there until they're perturbed,
Mm-hmm.
and then they'll start to potentially go somewhere else, potentially re-enter. But he attached himself to that idea. I was really inspired by that, and my first project was essentially a kind of like a stadium-sized generation ship that
Okay.
had almost no architecture per se. It was just a giant structural lattice
Mm-hmm.
that people could inhabit however they liked. So it was essentially a slum.
Mm-hmm.
It was an informal settlement, and I spun it for gravity, but I created I created uneven topography inside so that gravity was different wherever you were. There would be this like almost like field condition of habitation. Obviously, I've become more practical since then. But I defend my crazy start to this career. It's important for people to
let loose,
do what they need to do
in the control setting. Yeah. So let's turn to the project that first brought your work to public attention, the Mars Ice House. In 2015, it won NASA's 3D printed habitat challenge. For our audience, could you give a brief overview of the core concept behind using translucent water ice as a primary building material on Mars?
Yeah. Well, first it was an 8-person team that was comprised mostly of people who I knew through Columbia. And we were basically getting together in the office of Clouds AO, who was part of the team, and just sketching and, coming up with ideas. And for a good part of that design period, I was in Greece working remotely.
Cool.
Yeah, no, man, Mars Ice House is a bit of a dream because it's this project that was kind of created a weird genre. It almost created a genre of like it's kind of like upright, bright, sort of I guess beacon, iconic space architecture. I don't know. I'm not sure. I think most things before Mars Ice House. I'm not saying all of them, but most things were I think low, buried. Whether it's underground or it's kind of an aluminum can on its side covered in regolith and some wires going out to solar panels and I get it. I'm not saying that we make some engineering breakthrough. This was a speculative project, but there's a lot of rigor in the speculation, and the ice component was kind of twofold. It's one is the realization that ice will let through visible light, but actually filter out a lot of harmful radiation. So that's one. I think everyone, not everyone, a lot of people know that water is, because of its high hydrogen content, pretty good shield for heavy ions. You don't really want to shield with heavy elements because you'll get secondary radiation. So the current candidates for radiation shielding are like, plastics essentially.
Yeah.
Polycarbonates and things like that, like low atomic weight materials. So
because aluminum,
that's
let's say,
one.
produces neutrinos as a
Right. Yeah,
secondary
it
radiation.
creates problems. Yeah, it does shield some, but it also gives you something worse. So that's the first sort of component of the ice was like, huh, that's interesting. What else can ice do? The other thing that kind of tipped us to over the edge of actually making that decision was the triple point of water was very close to the actual, like the water that exists on Mars was already close to the triple point. So the triple point is that point at which you can become a solid, liquid, or gas by either changing pressure or temperature. Basically, we said, well, if we know there's solid water on Mars, but there's not much liquid water on Mars, and the reason there's not much liquid water on Mars is because the pressure is too low for there to be liquid water, but certainly the temperature is not too low for there to be liquid water. So if we could actually pressurize water but leave it at the ambient temperature, we could actually have liquid water that would then freeze. So basically, it's kind of like a way of taking solid ice, turning it into a feedstock, and then by putting it in a pressurized environment, saying, okay, we don't actually have to refrigerate this. We don't actually have to keep this cold for it to stay ice. We just have to protect it from sublimation.
Okay.
By putting it inside a membrane. So that was like when those two things combined, then we kind of started to think about the process, the sort of the concept of operations of how this thing would come to be on a planet with no people, no industry, nothing. So we outlined it. We basically had robots that would go out and mine ice. We had robots that would stay indoors and print the shell under a membrane, and we had this whole thing kind of happening outwards from a lander. So the lander was kind of your seed that grew this structure, if you will. And I'm still getting emails from the team that did that project because that project is being exhibited around the world still. It's like,
It's a
we've
beautiful
made a.
design.
Thank you. Yeah, it's kind of actually it's at the Smithsonian right now, and I've lost track. Like I've lost track of where it is, but I get emails of like, here's a picture of it in this museum. Here's a picture of it in that museum. I've had a chance to go see it in Spain
Mm-hmm.
and give a talk there about it. So it was really cool. It's been cool. It's kind of the gift that keeps on giving.
So if you were to reboot the Mars Ice House project today, with 2025 technology and knowledge, what is the single biggest change you would make to the design?
Well, I would make it more feasible.
Okay.
Certainly, if it was me that today I came up with this idea that hadn't been done, and it was ice, and it was on Mars, and assuming I wouldn't talk myself out of it, I would certainly make the form more achievable, because it does have some sort of edges
Mm-hmm.
that are hard to justify, like actual edges, sharp edges
Mm-hmm.
that are hard to justify.
Are you talking about the external shell or inside?
Yeah, the external shell. Yeah, I would also probably do a little bit more reflection about what it would feel like to be in a frozen structure. What kinds of clothing people would need to wear, if they could have personal heating devices that basically made them comfortable. So, maybe there's an extra dimension to the project that has to do with like their garments or the outfitting or the interiors of the living spaces that are in the central tower.
Okay.
So, yeah, that's probably the two things I would probably change about it.
Cool. Let's now move to 2019. You led the Marsha project to victory in the final phase of that same NASA challenge. Tell us about the fundamental shift in the material and architecture strategy from the Ice House to Marsha.
Well, after Marsha, there was some experimentation and tinkering with ice by the team and by some friends and consultants. And I think we were all interested in this ice thing. In fact, we were hired to do kind of a feasibility study for NASA,
Mm-hmm.
that someone had seen our project at NASA and hired us to like consult on the design and
Mm-hmm.
the structure. But this was a more feasible version of an ice habitat. So
Mm-hmm.
instead of printing ice, you would just harvest it and basically inject it into pre-made membranes.
Mm-hmm.
And so it was more like filling a big like inflatable mattress with water, and then it was this dome shape. So there was already a kind of like exploration of, well, okay, how could we do it like in a lower risk way,
Mm-hmm.
with things that behave more predictably than printing water. But I, the project that I did in phase 3 of the Marsha project was for was for an employer. Like I was
Mm-hmm.
employed by AI Space Factory.
Mm-hmm.
The project for the Mars Ice House project was independent. We
Mm-hmm.
just we just gave ourselves a name. It wasn't a company. It was a consortium of people. I had the opportunity to lead and author a whole new design based on everything that I felt like I learned.
Mm-hmm.
And in a way, that was my answer to your other question. How would you do Mars Ice House? Except it wasn't that I didn't keep any constraints
Mm-hmm.
like the ice, like I did to answer your question. But it was
Mm-hmm.
just like, well, how do we really want to do this? And I also read the new rules, and the new rule book had a scoring rubric for material selection, and it basically it basically prohibited the use of ice as a structural material.
Okay.
So that's actually, I just remembered that.
Mm-hmm.
I had totally forgotten that detail. But they allowed water as a binder or as an admixture, but not really as a primary material.
Mm-hmm.
And I did get the sense at the award ceremony for Mars Ice House that we were a bit of a controversial winner. The objective of the first phase was to make an architectural concept,
Mm-hmm.
and we were deemed to be the best. But the next one was all about, like, can this actually be prototyped
Mm-hmm.
on Earth at a 1-to-3 scale,
Mm-hmm.
in a room temperature? So you were not allowed to make a freezer to simulate Martian conditions. You had to prototype this in room, basically normal, Earth pressure, Earth
Mm-hmm.
temperatures. And yeah, that was that was kind of the starting point of this, and it was less of a decision on my part and more of just like, okay, let's keep this 3D printed habitat exploration going. How would I do it given the constraints and boundary conditions that I'm being given by the competition?
And what material did you end up using? Polymers, right?
Yeah. So there was kind of a fork in the road where we had to decide if we were going to go the cementitious route or the polymeric route. Cements are mostly water based. Large quantities of water go into mixing cements and concretes, and there are some exotic concretes that don't require as much water, and there's something called sulfur concrete, and there's sulfur on Mars, but no one printed sulfur concrete on Earth. It's not something you just go do, it's probably not, it wasn't really an option practically anyway. So I talked to consultants, I talked to professors, PhDs. I just tried to get an idea of what were the advantages and disadvantages of each, and I made the case to my bosses that we should go the polymer route, and we did. And from there, it was up to us to formulate that material. We don't have a polymer factory, so we basically had to ask for material donation from a polymer maker. So we contacted a company called Techmer PM, who supplied plastics for one of the teams in phase 2 of the competition.
Okay.
And we had basically a few conversations with them where I'm like, look, I want to make this a biopolymer because I believe that we could have the ability to grow plastics on Mars using organic materials rather than chemically synthesizing them from the atmosphere and the regolith and stuff. Perhaps we could have bioreactors that metabolize this. And I said, well, let's pick PLA. PLA is a a byproduct of a biological process. It stands for polylactic acid. So
it's the
lactic
same
acid is a
we have them in
biological
rolls for the 3D
byproduct.
printers, right?
Yeah, exactly. It's mechanically not the greatest material. It's pretty brittle, but great if you have a 3D printer at home and you want to print lots of things. It's like the least toxic. It actually smells kind of nice sometimes. It smells kind of sweet compared to ABS or nylon, which smell like burning rubber, And so how do you make PLA stronger? How do you make it ductile and increase its ultimate strength? Well, you add fibers to it, So we basically asked Techmer to make us 2 batches, and they made us a batch that had 40% plastic and a batch that had 70% plastic, I believe. Sorry, I got it backwards. 40% fiber and 70% fiber, I think. And we had them make us coupons for structural tests. So we did a tensile and crushing test at a place in Boston. And yeah, we got much better results with the 40% fiber. So it ended up being 60% PLA, 40% chopped basalt fiber. Basalt is a volcanic rock, which could also be found on Mars. And that's, all these things come together. You decide, oh, we want to print with plastics for these reasons. Okay, let's pick the bioplastic. Let's pick the chopped basalt. Where on Mars can we find basalt? Oh, in these latitudes and these formations. So let's just say our project goes there. And yeah, and then we just got running. They basically would sent us these cubic yard boxes full of pellets to our prototyping place in Boston, which we were using for like the 12-week prototyping period. And I mean, this is all after the design phase. Design phase was 6 months long. We didn't even know if we were entering the prototype phase yet. And once my bosses David, they were both named David, they were just like, we're doing this, we're gonna go for it, we're gonna take the risk. Then we were off to the races, and we just somehow slapped together a robot that could do this.
Yeah. So the final stage of the competition was live, like it was a live head-to-head construction trial. it was filled with successes and setbacks for all teams. Take us back to the final minutes of the build. The clock is ticking, your 3D printer is nearing the top of the structure, and your team suggests stopping to place the skylight. You overruled him and pushed to keep printing. Tell us how it felt those last minutes, and what was the calculation you made in that high stake moment?
Okay, so put yourself in my shoes. I'm the team lead.
Mm-hmm.
I got maybe 10 people there
Mm-hmm.
on our team.
Mm-hmm.
My two bosses are there.
Mm-hmm.
There's like 4 students from University of West Virginia. I think they had lent us a piece of equipment. They were there helping us, and then our core team was like another 4 people, 5 people. We have a data set up.
Mm-hmm.
We have 3 days to print, 10 hours each,
Mm-hmm.
and we are printing until the last second on day 3. So sometime on day 2,
Mm-hmm.
I have a back spasm from stress. I have to leave. I'm like hobbling on their shoulder,
Mm-hmm.
getting into a taxi, going to a massage place, coming back, feeling a little bit better. When I left, I took off my yellow wristband they gave me to know who the team leader was. I gave it to one of my teammates, Chris, and I was just like, I can't stand up. Like, so there's like a good amount of intensity in this and stress.
Mm-hmm.
And yeah, just to give you before the last minutes, just to give you a sense of what it's like. Like, we had a keep out zone where the printer was. We had a control station where we had our laptop, and we had some hardware, like, big red button, emergency stop button for the robot. We of course could intervene, but because this was an autonomous construction competition, every time we intervened, we had to notify a judge, and they had a stopwatch. They recorded every single intervention we made, whether we touched the robot, just messed with the laptop, or we stepped inside of the cell.
Mm-hmm.
And so we ended up getting like point deductions every time that happened. At the end, we had, and I'll give you an idea of why we would intervene. So one reason to intervene is that the machine just stopped running. Like, it just timed out.
Mm-hmm.
For some reason, there was this strange thing that we had never encountered. Maybe there was too many lines of code for the program we were using, and it just stopped. And the way to fix that was just to be alert. So we had to be like constantly watching this thing, because any moment it could time out. And when that happened, we had to basically stop the extruder, which was on a separate controller. We didn't have an all-in-one thing. And then like quickly just like pause and play the software. So that was one. Another instance was if the machine was printing, if the plastic was slumping over the edge of the wall because we were running too fast, and by the time we passed over it again, it was not cool and hard enough, then we would change the speed of the tool head. And if you change the speed of the tool head, you have to also change the extrusion rate if you want to maintain a constant bead thickness. So these are the things. Another thing is, like, if a window looks like it's didn't get placed correctly in the structure, then if you run in there and fix it, that's it. We didn't have to do that, but those are some examples. If a sensor falls off, tape it, whatever. Like, so this happened for 3 days straight. And at the very end, for those who may not remember the shape, it's basically like an egg, like this. And that means that the shape is getting, the circular cross section is shrinking and shrinking and shrinking. And it's shrinking so that at the end we place a skylight that we had kind of cut ourselves and made out of steel. If we had placed the skylight before we got to that critical diameter, the skylight would just fall through to the floor. Those were the last few minutes of the print. We knew that every single layer we completed, we were closer to supporting our skylight. And yeah, it was definitely intense, but at the last possible moment, we printed until the last possible moment, and then we let go of the skylight, and the skylight kind of landed, and then it did a flip and it fell. So I think what happened there is that we actually did clear the diameter, but we didn't place it on center. And when we removed the arm, it started to tilt a little bit. And when that tilt happened, all the weight of the Skylight was on these 2 points on the end.
Yeah.
And the plastic was a little bit soft.
Soft. It hasn't.
And it fell right through. And it was just like, that was definitely a moment for hugs and back pats.
Yeah. But you recovered with the stress test, right? With the crash test. And you
did you see the video of that?
Yeah, of course. Yeah.
Yeah.
No, I can see expression on your face and on the team, and then but thankfully the crash test and the stress test at the end.
It was one of the most memorable moments in my career when they used like a, I don't know, 40 ton, I don't even know what it was, this giant excavator, and they just pressed the top of it, and we're like, is this thing on? What's going on? And then you see the crane starts lifting off the ground, and at that point they just said, okay, you passed the test. Like they didn't keep going. They just So, and mind you that the structure was probably proportionally like an eggshell. It was that thin. It was in its bottom half, it was 20 millimeters across, and on the top it was 8 millimeters across. I think I got that right. But yeah, it was super thin.
Okay, so in 2020, you authored a paper for the Open Lunar Foundation on lunar landing pads, framing them as a critical shared infrastructure. This was right as NASA's HLS, the Human Landing System competition, was starting. We've since been seen multiple lunar landers, both private and national, fail in their final descent to the moon. How critical is a prepared landing pad to the success and sustainability for a long-term lunar presence?
Yeah, I mean, think of it this way: the lunar surface looks benign, but to land on it, you're basically shooting gases at high speed in the direction of the lunar surface, and if you don't do something to that ground, you're basically turning the dust and regolith into projectiles, high velocity projectiles. Furthermore, your benign moon, which looks pretty serene, doesn't have an atmosphere, and it doesn't actually slow down any of these things. So theoretically, and we worked with one of the preeminent physicists who works this problem, Phil Metzger. Theoretically, you could shoot a piece of regolith, a piece of dust to the right, and actually it'll hit you on the left, because it could go all the way around the moon. This is a bigger theme in space architecture, especially surface architecture, is you're basically landing something in a place where there's no infrastructure at all. And when you become aware of the risks, like the landing pad risk, for example, you realize that infrastructure is really important. There are things that must receive a spacecraft. It's not just you can land wherever because you're on a rocket. And so I think it's important. And, there's been a lot of studies on landing pads since. There's been competitions. It was a great time working with the Open Lunar Foundation. I was part of their first research fellow cohort, and they continued to definitely set the bar for what a collaborative lunar future could look like. It was great to have to look at the landing pad problem in that context. And this was a period in my career where I was like transitioning between being at AI Space Factory and being at Blue Origin, and it was just like one of those just open-ended projects that is adjacent to space architecture, but not space architecture per se. And I think anyone who's interested in space architecture or is already in the field will recognize what I'm saying here. It's like, you can't always work on habitats, because habitats are a tiny fraction of all the money spent in space. And if you can manage to always be working on habitats and getting paid, then you have some skills, some luck as well. And more likely you will be kind of shifting into the in and out of the things around space architecture. And this is one of those things that I think as a project, as a design study, really gave me another context to exercise my general technical aptitude, I guess, and creative aptitude. As I don't know if you saw the second paper where there was like these designs for landing pads. So here are four radically different ways you could make a landing pad on the moon. here's one drawing that explains the entire idea, and maybe some text that came next to it, and that's it. Like it was so much fun. And they were definitely game for that.
So let's move to your time at Blue Origin. When you joined the company, was your initial focus immediately on Orbital Reef, or were you brought in for a different purpose?
I was brought in anticipating that there would be an RFI, an RFP for space station.
Mm-hmm.
Yeah, at that time it was called Appendix K.
Mm-hmm.
Before I joined, there was this thing called Appendix K, which was the space station,
Commercial LEO Destination
RFP.
CLD.
Yeah. There was actually a short delay in the release of that RFP, which gave me some time, settle in.
Mm-hmm.
The first thing I worked on was lunar habitat study, which you're familiar with foundation surface habitat. That was another RFP that was out there, or was kind of like a looming RFP.
Okay.
That we thought was coming down the road, and we wanted to be ready with some answers.
Mm-hmm.
A lot of companies do this. They get word that NASA's planning to release a proposal, a request for proposal, an RFP for a thing, and so they put together a Tiger team to produce a feasibility study on this,
Mm-hmm.
and or a concept study, or reach some level of maturity ahead of the rush of a submission deadline, so that we actually kind of know what we're going to do, and then it's a matter of taking that to the executives and saying we have basically a starting point.
Mm-hmm.
We need this many people, so it's more of a workforce management tactic. And
Mm-hmm.
so I worked on a study, and then shortly after that, the Orbital Reef, what became Orbital Reef, started as a small team.
Cool. So the International Space Station has been the cornerstone of human activity in low Earth orbit for over 2 decades. What does the ISS personally represent to you as an architect and a space enthusiast?
You can't understand the ISS without having an appreciation for the history of other space stations that came before it. The first space station was Salyut. The Russians put up this single module station that was basic. It was not that capable, and went up in one launch. And that program lasted decades. Skylab was the first American station, and it was also a single module, but completely different, because it had Saturn V to lift it into orbit. It had these first two stages of Saturn V. The third stage was gone, and it was replaced with Skylab, and it was still unsurpassed in its diameter and its open space.
Mm-hmm.
So it's still something that space architects look back on fondly. That's going to change, with Starship and New Glenn and the payloads that they enable. But for now, we're still looking at those grainy videos. Salyut, you have a series of small stations. In Skylab, you have a kind of a one-shot, station
Mm-hmm.
with three missions, 3 visits. You can think of it as kind of like a very short-lived disposable single launch thing.
Mm-hmm.
And then you enter a new paradigm, which is Mir, which is the first modular station. So now you're getting single modules coming together, and the innovation of Mir was you had a node that received multiple modules, and you had a tiny arm on each vehicle that could move it around. The ISS was modular, like Mir, but it was in a way that Mir, it was very much defined by the vehicle that brought things, the space shuttle. The space shuttle, is source of many of the standards that we have today in like dimension of the modules, and like the cargo bags that are being transferred around, and the size of the payloads. All of that is basically derived from design decisions from the space shuttle, and you can't understand the ISS without really seeing the ISS and the space shuttle as actually like a kind of a dance between two different systems. For me, what the ISS represents is this kind of culmination of the civil space station era, which is that countries began, the US and Russia and USSR began by launching their own space stations, and then they started to scale up in their ambitions, and then what ended up happening was they joined forces. This International Space Station, it became the culmination of civil spaceflight, like lots of modules, lots of countries involved. We're all riding on each other's spacecraft. We are up there collaborating and shaking hands. And from a technical perspective, the ISS is as much about assembly as anything else. The assembly sequence was not linear in any way. It was like, you don't like start with the ground floor and build up to the second and then go up to the third and then put the roof on top. It was there's a first module, there's a second module. You move the second module over here, then the third and fourth come, and then then the fifth comes, you move the fourth one somewhere else. We
The
have
trusses
our
come,
power system is now pointing zenith. Oh, we're going to move it to the port side. Oh, we're going to add another one to this port side. We're going to add another one. So it's basically like this time lapse of almost like a child figuring out a Lego set. And that to me is like, we're not going to see that for a while because it's very, very expensive to do things that way, even though there's a lot of reasons why the ISS is designed the way it is and a lot of lessons to take from it as a space station designer.
Okay, so the ISS is scheduled for a controlled deorbit in 2030. From a vantage point, having been inside the development of its potential successor, how real is the risk that the international community, excluding China, of course, will face a gap in continuous human presence in Leo?
It seems unlikely that there will be a gap. This notion of a gap, though, is kind of BS. Though it's a bit of a symbolic thing that. So what if there's no American blood in low Earth orbit for 6 months? Like nothing changes in the world, you know. It's purely symbolic. It's just the embarrassment that we didn't plan to have a continuous presence. We kind of went through that already between the ends of the shuttle and the start of Dragon,
Okay.
where there was, I think, 9 years there where there was no American owned launch vehicle, and we had to hitch rides on the Soyuz. That's really just pride, you know. So I don't really care too much about the dialogue or the rhetoric of a gap. It's not that significant, but I don't think it's likely anymore
Okay.
because there are
Axiom
some.
also is advancing.
Yeah, exactly. There's just players now. There's people and they're competing with one another. And what's really cool, and I think what is meaningful more than this gap thing, is that for the first time, we stopped talking about new space, right? This term new space was this thing that people talked about 10 years ago, but we don't really talk about it anymore because it's not new anymore. In fact, now we have the children, not literal children, the children of these new space companies starting companies. Like now we have the second wave of commercial space already. Like Blue Origin has been around for 25 years. SpaceX been around for about 25 years as well, like maybe 23 years or something. So more significant to me is that we're already in the second wave of commercial space flight where people who are the leaders of the companies of the future are disgruntled SpaceX and Blue Origin employees.
Yeah. Yeah. Building the
People who
ecosystem.
weren't listened to and wanted to do things their way. You know, look at companies like Relativity, those are ex Blue Origin. Stoke Aerospace, that's ex Blue Origin. They're both doing things fundamentally differently at an architectural level, like vehicle architecture than their sort of parent companies, if you will. Obviously not parents, but that's how they were formed. And the folks at Vast are heavily collaborating with SpaceX people. There are lots of ex SpaceX people there who are leadership positions, and yeah, that's the exciting part for me.
Yeah, it's happening also in Europe. The exploration company, also the employees are ex Airbus employees.
Yeah,
Yeah,
circle of life.
exactly. So Orbital Reef was born, as we discussed, out of NASA's commercial LEO destination program. What was your specific role in the initial concept phase, and what was the single most difficult architectural challenge the team had to solve to make the proposal viable?
Hmm. Well, my role was Orbital Reef, before it was called Orbital Reef, started as like a 3-person charrette on the whiteboard once a week. And it was myself, Roger Ramsey, and Makoto Air. And we were basically, and also Robbie Gittin, we were basically just standing around a whiteboard. This is peak COVID, where we had to get permission from our vice president to go into the office because people were scared. People didn't. There's companies too. They didn't want people getting sick and dying. Don't ask me if I got permission, but we were supposed to get permission to meet, and we met, and we were with our face masks. And this was that critical period where I actually learned how to actually configure a space station. So that was just like the 4 of us. We went through so many ideas. We had certain approaches to things, that other people had other approaches to things, and we were learning from each other. It was great. Early day stuff. At some point we had, I think, 8 what we called concept seeds. A concept seed is just like a 1-sentence, like a nickname and a 1-sentence, like, here's what this thing is. So for example, we had a concept seed called the Whirly-Dirly. The Whirly-Dirly was an artificial gravity space station.
Okay.
We had a concept called Be My Neighbor, which was like a concept where we were actually not the prime. We were actually just joining, another station's core module. There was some, cartoon whiteboard level configuration development for each of these. The thing that I appreciated the least at that time was how the sun moves in the sky in low Earth orbit.
Okay.
Like, there are no months, in the Earth's orbit, but turns out it's about that long. And your solar tracking and thermal system has to basically be designed in certain orientations. And I didn't appreciate that in the beginning, but years later, when we were in the actual, we actually had to prove that these things worked. Then that's when I did so much of my learning on the configuration issues. And you asked me what was like the single most difficult thing, and I would say it's not that one thing was the most difficult, but it was a multivariable problem where all the variables are connected. It's not a zero-sum design game, but it's you can reach the limit pretty quickly of how much you can push this group of variables and without sacrificing the other set of variables. One of the big ones, I guess, this may not come as a surprise to anyone. There is something that is zero sum, which is the volume you have under the fairing. If you're trying to launch a station that is a single launch, that has all of its power systems and docking ports and pressurized volume and antennas and everything else into a single launch, then you will quickly find that it's very hard to have a station that is both abundant in power and also abundant in volume. So a lot of the debates ended up centering around, like, what is more valuable, power or volume? Power or volume? Obviously, we know mass is the problem. It's always constraining us, but that was probably like maybe the most frequent and most frequently encountered trade-off to do.
Okay, so a tweeted photograph from the project, from the from the Orbital Reef, showed you and your team inside a full-scale mockup, revealing an interior large enough for 2 levels. This is a radical departure from the single corridor scale of the International Space Station. Tell us about the design thinking behind that decision.
Yeah. Well, Orbital Reef, that mockup was about 6 meters across, I think, or maybe close to 7. It may have been like 6, let's just say 6.5. The big idea behind one of the big ideas behind Reef is that we had New Glen's 7-meter fairing, which was, it really enabled much larger modules and payloads than like any other rocket could. So we kind of decided, well, we better make that a differentiator in the design. So let's maximize the diameter we can fly. In reality, you can't fly something that close to the inside of the fairing. You have to leave a gap for vibration. and insulation, just physical movement. Your payload is going to move, your fairing is going to move, and they can't touch each other. So 6 meters, probably the most you could do in a 7-meter fairing. That still is a significant improvement on the constraint of the space station, which was the space shuttle's payload bay. It was about 4.4 meters. 4.4 exterior diameter.
For the
so
module,
the inside, for the module. So the inside, let's say 4.2. After you have shielding and other things, and then the corridor inside of that is basically what's left over from all the equipment, and that ended up being about a 2.1 exactly. So basically, there was a period in the design of Orbital Reef where there was certain leadership saying we got to maximize the diameter, making that case. And then there were other people who were saying, but do we really need that? And these are hard to build. Can we get away with 5? Can we get away with 5.5? And also not just space, but mass. Let's be real. The diameter of a module is a driving variable in structural mass. So that was a debate. So I decided that I had to write a memo because Blue Origin is a memo culture. You write memos and you send them to your leadership, and then you have a meeting about them. So I wrote a memo simply called Orbital Habitat Diameter. And in it, I attempted to figure out where on a diameter, on the growth of a diameter from ISS upwards, did a step change occur in capability. I defined capability primarily in 2 ways. One was the raw capacity for storage, or just volumetric capacity for equipment, stuff, anything. And the second was the potential for spatial zoning. The ISS, as you point out, is a single corridor. That's the type. Every function is in a straight line. I think of it as like a necklace with beads. If you want to get to the 4th one, you have to pass through the first 3. There is no second dimension. Or third dimension. It's a one-dimensional space station. The third and second and third dimension, they occur at the nodes where you can make a left turn and go into a different module. So there are some dimensions in the space station, but not in the module. Especially if there's a strong drive to have a single module space station to reduce costs and operating, complexity, and you definitely want to maximize the diameter as much as you can. My argument was that step change occurred at 6 meters. So that actually happened to be right about what you could launch in the New Glenn. And of course, some payloads may be able to go beyond that. So if you're planning a payload on New Glenn, don't quote me, because it depends on the payload's rigidity, its height, and also what kind of protrusions there are, and if you can make exceptions for them in the insulation or something. But we decided I came out with this result that said 6 meters is actually it represents a step change and an advantage that we should pursue. And then once you have, and the reason there's a step change is because you can actually have multiple spaces happening in parallel. You can go around a space. You can have a space that's truly private. It's at a dead end, for example. The way that in a house you make turns and you can get to a room that's private, or you can have a room that's central to the house and other functions come off of that and people gather there. You can actually start doing that if you have 6 meters. Can you do it at 5.8? Yes, but it's tight, right? So I used some anthropometric standards to determine that, which I found were acceptable, and also followed with some heritage in the space world, like the depth of a locker, for example, was factored into that. So yeah, that mock-up is what you see in that mock-up picture is like there's a deck up top and there's a lower deck. The reason there's a deck is because we were decided at that moment on a horizontal orientation because of there's a couple of reasons. One is that the attitude of a spacecraft, of a space station, is going to basically try to be axial into the velocity vector in most cases, and that's the easiest direction to grow in because you're not increasing your drag area.
Mm-hmm.
And we also felt strongly that the view of Earth was one of those that people, no matter what they were doing in space, would want to do there, is to have a lot of time viewing the Earth. If your module is oriented, and this was like a direct view of Earth, right? So we wanted a lot of barrel surface area facing the Earth. And then from a spatial architectural perspective, having a kind of a horizontal orientation that aligns with the Earth being up rather than down was actually a pretty strong desire from the architects. The sky on Earth is the source of light. It's the source of color, and of course, light and color that change throughout the day. If you think about what the Earth is in space, it's actually performs a similar psychological and almost illuminatory function, and it's actually a more interesting sky than the one we have, frankly, because Earth is the most interesting thing we know of. So we've essentially, all these things come together for us wanting to position the Earth as our sky. And if Earth is a sky, Earth is overhead. And if Earth is overhead, then there's there is a down, and it's in the other direction. And then what's ahead of you then wants to be the long sight line.
Okay.
Much like on Earth, you have a horizon, you have a long sight line this way, a visual field with interesting, relevant things to you, right? And so that was what orienting the module horizontally got us. Now you could orient the the module vertically, meaning that you could just take it like this and slice it, and you have circular floors. And I think that was certainly has its advantages for building a mockup. You could just build these circular mockups one next to the other. You don't have to build a giant cylinder turn it on its side. So there's some economy there. But I was adamant that if we designed the station to how easy it was to mock up in one gravity, then we were doing things backwards. I came into Blue Origin well aware of how much effort was put into like Hollywood films for spacecraft. Like if you look at how they built the 2001 Space Odyssey spacecraft interior, they made a hamster wheel where the camera was stationary at the bottom, and they rotated the whole thing, and they had the running scene. To me, if someone puts that much money into a fiction, then a company run by a billionaire would put as much, if not more, into the real thing. But I was wrong about that. The mock-up ended up being the tail that wagged the dog, I think. So we'll see. Like Orbital Reef is still in the dark with respect to the public eye. Like even I don't know what it looks like right now. So I just know how it changed. So
okay. So beyond the sheer volume, what are the most significant architectural differences between the design philosophy of the International Space Station and Orbital Reef?
Which differences? Just besides the volume?
Yeah. What other significant differences you think there is between the International Space Station and Orbital Reef?
And the biggest one, I talked about all these orientation decisions and the Earth, the role of the Earth. The other big thing was Orbital Reef was inching towards a bit of a commercial real estate model, where instead of kind of each module just plugging into the next in a way, and then people like kind of sharing everyone's sharing everyone else's space for different functions, and like the Europeans bring this lab and now everybody uses this lab. It was a little bit more of like, yes, we could do that, but if we started with a central core module that operated as a piazza or a town square or a common area, that it did have some core services that it could sell to the neighboring modules, but it would also be like the most desirable place to be because it had all these Earth windows, it had amenities, it had like dining and gathering areas. So think of it as almost like it was a systems infrastructure, but also the experiential center. And I think of the piazza is my favorite metaphor, because the piazza, it looks like nothing. It's open space. It's a square, and if you look at it, you're like, well, there's nothing here, right? But there's so much here, because all the neighboring buildings face onto it. At their ground levels, they all have shops and restaurants and then of course in the center there's things for people to do. Like there's a fountain. It's a focal point where people gather and they smoke and they play music and
Yeah,
and
for communal
they
interaction.
yeah, and this is what a city is like. So in a way, there was an injection of a bit of the urban code into the space station code, if you will. A little bit of like, can we actually add some of that code in? And that was the idea. And if you could then have a specialty module be birthed radially. Could be all labs, entirely labs, because there's another module to the other side, which is entirely a dormitory.
Okay.
And this, of course, is not the specialization by module is nothing new. The space station was originally conceived to have a habitation module and a lab module. Value engineering and budget cuts produced a sort of station where you shit where you eat. It's a station where you wake up, you pop out of your room, and you're in the lab.
Yeah.
It looks like any other space. There's a bit of a the personal privacy that people have on space station is essentially limited to their private bedroom. There's no there's no other gradients of experience.
Okay, so at some point, does the designer realize that the station isn't just for the crew, but it's fundamentally a machine to serve the science and technology experiments and research being conducted? And how did that realization shape your design priorities?
It's not so much a eureka moment that I had, but I did observe that there was different approaches to this. One was kind of space first. I mean, when I say space, I mean interior spaces. A kind of a space first approach, which I tended to take. I tended to shape the space while protecting for equipment space. I would have my equipment. I'd understand what it generally required in terms of its space, adjacencies, mounting locations, but I would just take an empty module and I would think about, well, okay, given all these things I have to put in here, and given the potential that this module has for being a nice place to be, how would I architect this? What spatial gesture would I incorporate? The ISS, if you're just talking spatial gestures, the ISS has one gesture. It's a square running down the middle. But when you have bigger modules, you have way more options, so they deserve exploration. And you could offset your corridor to the one side and then have other rooms and coming off of it. You can zone things not based on corridors and hallways, but just based on the shape of space and the dimensions of spaces, which might be smart because corridors make sense at a certain scale of building, but not necessarily at a small scale. But then there are egress requirements. So, you need to at some point demonstrate that you can quickly get to your escape vehicle, to your lifeboat. So if you have a zigzag path from the corner bathroom, and that's the only way to get out of the station in a timely manner, well, it may not be timely. So that's part of it too. So I think, yeah. So it wasn't so much of an eureka moment for me, but it was maybe the realization that the starting point of a design, the design vision that you establish up front, and you sort of you gear yourself up to champion that vision and also adapt it to engineering reality along the way. That's the way that you get good architecture, is by having a vision that is founded on reality to begin with, but it's also putting the right thing first.
Great. Your former boss, Jeff Bezos, has recently stated a vision of having 1 million people working in space by 2045. From your practical experience, what is the single biggest architectural or technological hurdle we need to overcome to make that vision a reality?
Well, it depends how long they're living there. and how long they're working there. If you were to say 1 million people visiting space annually, right? That's one thing. Then the most important thing there is the
Logistics.
the throughput, launch throughput. Like how many people, how many seats can you get up per day at that level? It's like, can you make a real spaceport with like multiple gates and a ground crew and like just constant rocket launches essentially? But if you're talking about people, this sort of idea that I think when Bezos first said that, he was showing these O'Neillian visions. O'Neillian visions are these kind of fictional, these big things, kind of like mini planets in a way. I mean, there was a time when the human species did not know how to make new chemicals. We were just stuck with the things we found, and then we discovered a way to direct energy at matter, and we could synthesize chemicals. Like, most of the things in our lives today are synthetic. They don't exist anywhere, except in our factories. There was also a time when we did not know how to split an atom. Now we can make new elements. There are elements on the periodic table that can't exist naturally, and they can exist because we decided that we can make them. If you think about, we're climbing this ladder of science where we, first we can manipulate matter, and then we can manipulate chemistry, and then organic chemistry, and then we are at this point where we can make these primitive cells. Like, we can start manipulating life. We're tinkering with genetic code. So what's after biology? It's ecology. Ecology is, we are far from a capability in ecology that's analogous to the capabilities we have in physics and chemistry, and even starting in biology. Like, and what I mean, in order to create artificial ecosystems, you have to know how to make one. Like, you have to have discovered the code, you have to have reached a certain level of knowledge and control over a natural phenomenon that you can actually reproduce it outside of its natural context and keep it going. And we're not there. So
but I think now you're talking about the bioregenerative life support systems, the closed loop bioregenerative life support systems.
Sure. I'm not necessarily talking about those systems, because I know those systems exist as engineering systems. But when you're talking, you asked me about millions of people, we're not talking about 1 million spacecraft, right? With one person in them with a CO2 scrubber. So, like when founders say big things, remember their incentives.
Yeah. I'm actually interviewing a doctor who's doing research on reproduction in space. So that's interesting too. Cool. Viewers shouldn't forget that you also contributed to the Blue Moon Lander program, right?
Yeah.
So what was it like?
Yeah, that's actually the last thing I worked on at Blue. I worked on the flight deck and the interior of the human lander. Yeah, that was so much fun, because a lot of my career at Blue was spent on configuration of space stations and at the architecture level. Like, if not in the interior, I was playing with big building blocks, but the flight deck was this intimate thing where there's like you're looking specifically at what people's eyes can see at an instrument panel, how much they have to turn their head to see out a window, how much they might have to rely on touch alone without looking at their controls, the impact of wearing a pressurized glove or an unpressurized glove on an inceptor, like the lighting environment, how you hold people's attention, how you bring relevant information to their immediate attention, and put less relevant information in the back. And I was lucky to work with some smart people, and like pilots, experienced designers, industrial designers. the pilots would want a certain kind of people who have experienced flying spacecraft or helicopters or fighter jets. They're all in the same team and they're all have different philosophy. So that was fascinating. Yeah, I just had a call with another colleague who told me, it's like, yeah, like with a former colleague at Blue who's still there, and mentioned to me that some of the groundwork I laid is still there. So that's nice.
That's awesome. That's
Yeah.
amazing.
And that would be either Orbital Reef or the Lunar lander would be my first spacecraft, the first things I worked on to fly as designs. Like I've had some material samples go to space, but those would be the first like things I worked on as a designer. So
Yeah,
can't wait.
You'll join a very special club for people who have designed space that stuff that are actually went to space and people lived in them, like Mark Cohen.
Yeah. It's a small group, but growing, I think.
Yeah, hopefully. Okay, so let's move forward to the future outlook and the long-term vision. You've since moved from Blue Origin, and you've designed for Mars, the Moon, the Earth orbit. You've taken concepts from theory to physical prototypes, and hopefully to space later. What is the next great problem, the grand challenge in space architecture that you feel uniquely positioned and personally driven to solve?
Well, I mean, I'll speak less about the problem that I'm driven to solve, because solving is, I think I don't see it in those terms, because I think I may have know too much. It's maybe not a thing to solve, but more of a thing to get in on, a thing to just really be in on, and be in the room. And I think that's maybe where the changes are happening. Is I mentioned earlier that there is a second wave of commercial space happening right now, and that will happen again, right? There will be a third wave again, and a fourth, and etc. So right now we're in this wave where commercial space flight is becoming the main show in town. For various reasons. But just to state the reality, we're kind of, this is kind of the show right now, is this commercial space. And just the rocket equation will tell you that it's much easier to get to Leo than to get to the moon, than to get to Mars. And so the biggest opportunity right now is in low Earth orbit. There's also a lot of risk there with a lot of the satellites up there and debris. These things do have some solutions to them that I'm not personally involved in, but I see commercial space stations as the next solvable thing. And I don't mean technically, but more business. You know, it's pretty much accepted now that space stations have been technically solved. They can still be improved, just like rockets were solved 50 years ago. They're still being improved, but the hardest thing now to solve for is the business of commercial space, especially human space flight. No, commercial space has been commercial in satellites for decades, and much of our commercial infrastructure now is resting on that, but human space flight is very difficult to make close in a business sense. So in my private work now, as an independent, I mean, that's what it's about. It's about how can we architect commercially viable human spaceflight, or commercially viable space architectures that begin robotically, or maybe there's a hybrid of human and physical, human and non-human presence. That's kind of, to me, that's the kind of the biggest thing happening now. And I actually think, interestingly, the commercial space station history is going to repeat itself and fast forward. We're going to start with single module, single launch space stations that take advantage of heavy launch vehicles, and not just taking advantage of those things, but they will be strongly driven to be zero assembly turnkey space destinations for business reasons. The International Space Station, with its multiple launches, like 50, 60 launches, obviously it was operating throughout that period. It wasn't like it needed 60 to begin, but every business, every person who actually believes they can trying to make money in space is going to push for simplicity. They're going to push for like operational elegance. And designers are very good at thinking about these things, about balancing constraints with value, balancing costs, concerns with the actual value to customer, because most companies will want to cut costs, but they also need to remember to add value, add value, add value.
The space sector has seen layoffs across the board and across multiple firms. What did this cycle teach you about career design in frontier industries?
Well, that's a good question. I don't take it too personally. Kind of like college admissions. It's a bit random. Like, yes, you'll generally kind of maybe get into schools you deserve to get into, but oftentimes you'll apply to 20 and you'll get into the top ranked school only, and everyone will also reject you. And that's just life, There's a lot of noise in these systems. And so, corporations they're kind of notoriously inefficient, and they don't really have a great way to track like the value of individual employees. They make a broad kind of herd level decisions, and they accept collateral, right? They accept casualties. So
Statistics.
I actually kind of see it as I see this in a kind of through a naturalistic metaphor, which is like Blue Origin is this forest, or maybe it's the canopy in the forest, and it's dropping fruits, and there's this, layer on the forest floor of smaller plants and medium plants, and they're all eating each other and decomposing, and like whoever Blue Origin lays off, whoever anyone lays off is going to have choices to make, and they're either going to and whatever they do, they're going to adapt, right? Some people will decide to form companies, some people will go work for someone else and bring that knowledge with them. And so that's what I mean. It's like it's an ecosystem of talent and knowledge and skills, and it's the circle of life. I guess it's the first time I experienced that, so I certainly had to learn these lessons through experience rather than through theory. Like, I'm sure someone who hears me say this who hasn't been laid off will be like, yeah, of course. But then when it happens to them, they're going to feel it differently. They're going to understand it differently. So yeah, the layoffs are there. It's just it's unfortunately how things work. Not saying they have to work that way, but yeah.
What does the saying goes? What doesn't kill you make you stronger.
Yeah, exactly. I don't feel like I've lost much. In fact, I look back on my time, not just at Blue, but the journey to get me there as just like wonderful and full of learning. That's the biggest thing. You got to learn.
Yeah. Jeffrey, if a listener is inspired by what you've just said today and heard from you today, what are, let's say, first 3 moves you recommend they make in the next 30 days to get into space architecture and this kind of sphere?
I think the best space architects will always be architects first. I wouldn't say go get an engineering degree and then go become a space architect. I'd say go study architecture first every time, because the architect by their nature is someone who can work with constraints, and in the simplest, dumbest way, like space architecture is architecture with different constraints. And they're working with different kinds of things and different systems, but even many of those systems are very analogous to the ones that you already know. So it's a plastic sort of, you just have to adapt. It takes time to learn and appreciate all of the constraints because there are so many. But have I said anything that's different about normal architecture? No. A rookie architect out of school doesn't know much, right?
True.
And they learn it through practice, and that's the same thing. So honestly, it's just architecture. It does, and just like any job and any career, you're going to go through a period of being inexperienced, and eventually you're going to be exposed to enough problems and have an opportunity to work on those problems that you'll become good, so and efficient. The good news is that spaceflight and space architecture as a, let's say, as a physical achievement, requires kind of every kind of person, lawyers and business people and recruiters. Like I can't, it's just like a microcosm of human ability. So we basically, there's room for everybody. I guess second piece of advice is be adaptable, because even if you set your sights on this thing, there's no guarantee that it's gonna work either at all, or there's no guarantee that it's gonna work on the time frame that you wanted it to work.
True.
Also, like your career is just one part of your life, so don't let it become the only thing that that gives you your sense of accomplishment and worth. There are other reasons to not work in. There are reasons to not work in space. For example, maybe you don't want to live in the United States. Like that's most of the space money is.
Mm-hmm.
But if you don't want to be here, okay, like that's a pretty good reason. The place where you live is a huge choice in your life. Like, so that's there's so many reasons to adapt and just be flexible. And also there's this also, I guess maybe this is my third piece of advice. They all connect, right?
Yeah.
The first one is be an architect. The second one is be adaptable. And the third one is listen to, people talk about like product market fit.
Mm-hmm.
You don't build a product that no one's going to buy. Think of the people around you as a market and yourself as a product, and ask yourself, like, what do people want you for?
Mm-hmm.
If they want you for things constantly that you don't want to do, ask yourself what that means. Does that mean that you're in denial about what your best talent is? Or is everyone else wrong and they don't get you, It's just like you got to be at peace with who you are and what you're good at. Like, don't pretend for too long.
Cool. Yeah, that's really deep. Are you at peace with who you are?
Yeah. Yeah, I
That's
am.
good.
I mean, I think I think people who know me can say that I I speak my mind. Like I feel like I know who I am. I know who I'm not. Certainly, if someone calls me an engineer, I don't let them call me an engineer. The matter, like the grain, the grain of my wood is not that, right? So yeah, like I certainly I think I'm certainly at peace. And honestly, frankly, I'm kind of unusual as a space architect, not just because of the luck I've had and
Mm-hmm.
the positions I've had, but because I don't have an engineering degree. Most space architects practicing have engineering degrees because they were either recommended to do so by a mentor, or they they actually like the engineering, like they enjoyed the process of getting the degree, which is fabulous. I considered engineering school because I knew that it would like make me a favorable hire. But when I reflected for more than 30 seconds on how happy I would be whilst in engineering school, I just said no. No, like that's not who I am. And I think I can succeed without that. So
Jeffrey, before we wrap up, is there anything else you'd like to share with our audience? Is there announcements? Where can you find you? When is your next cohort?
yeah, so where can you find me? I started a company called Different Systems that can be found at different-systems.com. And it's, basically you can contact me there. You'll also find on that website a independent course that I run on space architecture, which I just started a month and a half ago, and I'll be running in the spring. Sorry, I'll be running in the summer. I won't be running it in the spring, but yeah, if you've ever taken a design studio, it's modeled after a design studio.
Mm-hmm.
So it's a combination of, independent research, one-on-one mentorship, peer-to-peer learning, and like lots of presentations and practice communicating your ideas through architectural means like drawings, models, and kind of like that mix of verbal and visual and conceptual, and that architects are good at. So right now, yeah, I'm running that for the first one right now. The final review is in 3 weeks.
Mm-hmm.
In fact, tomorrow is the mid review, and I'm really excited for that. So that's actually a thing that kind of is accessible to anyone that I'm doing.
Mm-hmm.
The other stuff is I'm practicing as an architect on Earth-based projects and space-based projects. So I do like regular houses in Seattle with my wife, who has a firm as well, and I do like private consulting for commercial space ventures as well. That's kind of what I'm doing right now.
Jeffrey,
It's fun.
it has been an honor to have you here on the podcast. Thank you so much for sharing your insights and expertise.
Thanks, Omar. It was a pleasure talking to you too. Thank you.
To everyone else listening, this is the Omar Aleli podcast. Thanks for joining us and keep exploring.